Okay, welcome back Physics 20s to our next lesson in Chapter 8. We're going to be looking at pipe resonance, but first we have to talk about interference. So this is a string and it's connected on both sides, and if I send a pulse down it, we saw from before that it goes all the way to that side. If it hits a dense barrier or a new dense medium, it's going to flip, become inverted, and then it's going to come back. But we're going to look at now is if we had two pulses. So I'm going to have one on the left here going to the right and one on the right on the bottom going to the left. Now it's kind of hard to animate, but it would look something like this. Okay, so what would happen is they would come together, but when they meet in the middle, they're going to cancel each other out. So I'll draw this here where this is coming on this side and this is coming on this side, and their amplitudes add together when they're going to overlap. So say this was a height of something like 10 centimeters, positive because it's on top, and this is negative 10 centimeters. When they come and meet in the middle, their net amplitude is going to be 0 centimeters as they're going to add together, and that's called interference. If we had them both on top like this, and again, let's say this is 10 centimeters and this one is 10 centimeters, and they're coming towards each other like this, again, they're going to meet in the middle, but now it's going to be plus 10 and plus 10, and they would make a really large amplitude here of plus 20. All right, so that's how waves interfere with each other. Now we're going to look at how when waves interfere with each other, they do so at the right timing, so it's similar to resonance. So I put this arrow here to imagine you're holding on to the string right there, and you're going to shake up and down. Now you're going to shake up and down so slowly that the whole arc of the pulse that you create covers that whole string. So you go up, and by the time it gets there, it's going to bounce back and it's going to come back across the bottom like that. Now as that's starting to come back up in the string, you pull up once again. So you time it exactly so that when you send the initial pulse and then it comes back off the reflected, you pull it the exact same right time again, really similar to when the pendulum was swinging back and forth and we pushed it at the right moment there. Then we're going to be increasing its amplitude, so then it's going to go higher and then comes back again, and then we pull at the same time. So if we are adding energy at that point, we can get this to resonate by interfering with itself. The one going there and the one coming back are matched up perfectly if we keep adding energy. Otherwise, if it's just staying at that rate and we're just kind of keeping it going, this is called a standing wave. And this is how musical instruments with either air or strings are going to create their sound. That's based off their resonant frequency. So again, when we have this scenario, it's called a standing wave. It's based off the resonant frequency, which is based off the length of that string and how fast the wave travels back and forth. And how long that wave is, the wavelength that it has to be to match that end of the string, is kind of determined as well. So its resonant wavelength has to do with the length of the string. And the lowest frequency that this is going to occur at is going to be its fundamental frequency. And I say the lowest one because this can happen at multiple frequencies, and we can fit multiple wavelengths in here that's going to work. So I'll show you what that's going to look like. I could also shake the string up and down in half the time, and it creates a pulse like this. So I go up, down, and back to normal, and I create this shape of pulse. Then when that inverts, it's going to come back like this. I showed it going the wrong way, but it's going like that. So now we kind of have the same things we had before. It's fitting perfectly over top of another, but there's two of them. Now when I go here to here for the yellow, that's one wavelength because it's gone through the top and bottom, and then the green comes back through the top and the bottom through a wavelength. And if we can get this resonance to occur and keep moving our hand at the right time to create this right in the middle, it's actually not going to move at all. We can see at that point there's no motion up and down of the string. There's going to be the most motion right here in the middle, the peak and peak right there, or peak and trough right there and here. So we get movement right here and no movement right here in the middle. This is a standing wave as well. So just put the words up there, standing wave, but this is a multiple of that fundamental frequency. It worked with just half of a wavelength, but now it also works with a full one. And we can keep overlapping as long as it keeps fitting like that. This is called the second harmonic because it's the next one from the fundamental frequency. I'm introducing some of these terms like fundamental frequency and harmonics a bit early, but just want to show how it relates to resonance before we get into pipes, and then I think that terminology will make a bit more sense there and be a little bit more familiar. So fundamental frequency is the frequency that kind of fits when these wavelengths fit in this string, and harmonics is how many multiples. So the longest wavelength that's going to fit is the fundamental. Then we go up the next harmonic. We see here this fits as well. If we were to make it so another one would fit, I don't know if you can really see this well, but if it went up and down and up and down, that would fit too. And I go up or down and up and down and up. So as long as they kind of fit and overlap on each other, those frequencies will resonate. That one's the third one, and that would be considered the third harmonic. We'll see that again when we get into resonance on a string, which is going to be in a couple lessons from now. But this concept of self-interference and resonating frequencies is fundamental to the next 3 lessons. So I'm going to draw here, we have one wave going like this, and then the reflected one that comes back that looks like that. Remember, this is a standing wave. There's lots of peaks and trough here, but as long as they match up like that, this is a standing wave. And some terminology that we need to know is that whenever it is at one of these places that wasn't moving in the string, I'm gonna put circles on all of those. These are called nodes, right? And on a string, there'd be no movement of the string at that point. Now, opposite to that, where we have the maximum amount of movement is right here. This is moving the most up and down. So I'm just going to put some lines at the top here to show where those places are. And these are going to be the opposite of nodes, or they are called antinodes. Antinodes. Put an arrow to those on top, put an arrow to those in the middle. I'll just show that equilibrium is lined up the same here with all those nodes. And as long as they line up in this way in the pipe or on the string, which we'll look at how much fits in a pipe or a string just in a second, then it's going to resonate. So we're going to start with looking at pipes. And pipes resonate with an antinode, which we just mentioned, at the open end, and a node, it's actually not supposed to say anti there, and a node at the closed ends. As long as the wavelength fits the pipe like that at the open end, so let's say here is open, has an antinode, and then a closed end has a node, then a pipe is going to resonate. And this happens for all musical instruments. A trumpet is just an example of a closed pipe. Well, closed at one end. At this end, it's going to be open, but at this end, it's going to be closed by the person playing it. So how it's going to make a noise or resonate to make a noise is if the wavelength of the sound fits in that pipe so that there is an antinode at the open end and a node at the closed end. Let's draw what that would look like. So here's our closed pipe because it's closed at one end, and I'm going to reference this diagram from before. This pipe will resonate or make a sound as long as there is an antinode here at the open end and there is a node at the closed end. So looking at the diagram up here, you see, let's begin right here where there's a node. That would need to line up at the closed end of the pipe. Now, where do we first hit an antinode is right here. So that would make it look like this, like there. So the wave in yellow is going there, it resonates and comes back along the bottom. That's what fits for an open pipe, and that's what's going to resonate. Now, why doesn't it have to come to a point and then like invert to like come back across that pipe? You can kind of think of it before when we talked about strings, that if you go to something less dense, it's going to reflect erect. So I just kind of like to think of it like this. If we send the wave out this way, right, it hits, we're not going to some fixed medium like we were in the string. We're going to air, which is less dense than kind of like being in the pipe. So then it's going to come back erect, so on the same side like this. Then when it gets to the solid end, that's like going to something more dense, it's going to invert and go this way. Then it goes to something less dense, comes back on the same side like this, and it can kind of keep going back and forth like that. Not maybe the most accurate description, but that's how I kind of like to think of it. It usually helps to make sense for some people. Now it's important to look at how much of a wavelength this is. Well, if we're looking at this diagram at the top, to go up and down and back up, that's a full wavelength. So this is just a quarter of that. If I'm going to put lines here showing that's one wavelength, this is 1 out of 4 to this line here. This is 1 out of 2, this is 3 out of 4, and this is 4 out of 4 of a wavelength, because it has to go through the whole motion. So it's only a quarter of the wavelength that we've hit. So I'm going to write here over on the side, what's going to resonate is a quarter of a wavelength is equal to the length of the pipe, because the length of the pipe is from here to here. All right. Now that's not the only part of a wavelength that can fit. As long as there's a node and antinode, we can fit more. So let's get rid of those ones and say, well, if I don't go to that antinode and I still start at this same position, what's the next antinode that I'm gonna hit? Well, we already hit at 1/4 of a wavelength. Would a half work? Well, that wouldn't work because we're at a node. The next antinode we reach is at 3/4 up here. So if I put 3/4 in there, it would look like this. It gets sent there, comes back, inverts, goes out, and it's gonna look like this. So we have node, antinode, node, antinode. Again, as long as it starts with a node on the closed end, finishes with an antinode on the open end, this is fine. So now this is the 3/4 of a wavelength is in the length of the pipe. So that is our next one that's gonna resonate. Now I'm gonna introduce those terms again of harmonics and fundamental frequency. The lowest frequency or the longest wavelength that fits inside the pipe is called the fundamental frequency, and that was the 1/4. So fundamental frequency is this one. You can think of like the shortest amount of a wave that is going to fit in there. That's what the fundamental frequency is, and that's what it's going to resonate at first. As you go up, we're now going to the next harmonics. This is the multiple of the fundamental frequency. So this is the next one that's going to resonate. So you might think the second harmonic, but it's actually multiples of the first one. So the first one was 1/4. Now this is 3/4. So this is considered the third harmonic. And you might think, well, what happened to the second harmonic? An open pipe, or a closed pipe does not resonate at the second harmonic because 2/4 we saw there, it would be the same as a half, and that doesn't resonate. So it resonates at 1/4 of a wavelength, 3/4 of a wavelength, and the next one would be a fifth. I don't know if we can really draw this on there, but it would go all the way to there. I'll try and draw that in here. I know we have a lot of stuff already, but that would kind of look like going up, down, and up again like that. And then its inverse would be like this. I'll just put it with dotted lines there. Now this is going to be like from here to here was one full wavelength, and now we have an extra 1/4 too. So this is 5/4 of a wavelength is equal to the length of that pipe. That would be the fifth harmonic. And that would resonate as well. So what do we want to take from this is that 1/4 and going up every half after this is going to resonate in a closed pipe. 1/4, 3/4, 5/4, you could keep going up to 7/4, 9/4, things like that. I don't think you'll see past the fifth harmonic, but that's what's going to resonate in a closed pipe. So what are the questions going to look like? It could be like this. What is the fundamental frequency of an open pipe that is 80 centimeters long and the speed of sound is 343 meters per second? So all this is combining the theory that we just looked at with the equation V is equal to wavelength times frequency, okay? So this one says, what is the fundamental frequency? So already from here, I would start with this equation and say it's asking for frequency. So we must have some other information about this equation. Well, we already see that 343 meters per second is given to us, so that's velocity. All we have to determine now is the wavelength. And it says the fundamental frequency in an 80 centimeter long open pipe. Actually, sorry, we're dealing with closed pipes in this lesson. Let's change that to closed pipe. So let's draw a pipe looking like this. And it says the length of that is equal to 80 centimeters or 0.80 meters. Now remember, I just need to figure out what the wavelength is in this formula. So I need a way to go from length of the pipe to wavelength. And we saw this before when we wrote that some ratio, some amount of quarters of the wavelength was equal to the length of the pipe. How many quarters just depends on if it's the fundamental frequency or which harmonic it is. This one says the fundamental, so we know that the wavelength is so long that only 1/4 of it fits inside of here. If I was going to keep drawing this, this is how far the wavelength would be. It would be all the way like that, and only of 1/4 of it fits in there. So just looking at kind of the concept here, well, that means if the length of the pipe, 80 centimeters, is only 1/4, we just times by 4. We could go 80 here, 80 here, 80 here, and 80 here, and that gives us our wavelength. And that totally works. You can just times 80 centimeters by 4. If you want to look at the math way, we would have 1/4 of a wavelength is equal to the length of the pipe. We're trying to rearrange for wavelength. So how am I going to move 1/4 over there? Well, I'm going to times by 4 and divide by 1. Just like kind of taking the inverse to get rid of these numbers. Instead of dividing by 4, I times that 4 up, and I divide the 1 down, and I have wavelength is equal to length times 4. So that's all we got to do. We're going to take 80 centimeters, so 0.8 meters times 4, and you get 2.4 meters. Now I know it's getting a little messy here, so I'm going to wipe it out and rewrite our first part, which is V is equal to lambda frequency. We're trying to solve for frequency, so V over wavelength is equal to frequency. It says 343 in the question, meters per second. We just said this is 80 centimeters times 4, so 2.4 meters. And we're going to get an answer of 142.196 repeating hertz. So we would round that to, looks like we only have 2 centimeters there, so 1.4 times 10 to the 2 hertz for the fundamental frequency. So start with this equation here. Know that we're given this, we're looking for frequency, so all we need to figure out is wavelength. And we looked at the relationships for some quarter, put a question mark there, some quarter of a wavelength is equal to the length of the pipe. And you just have to figure out which harmonic it is going to be. Now it could ask you the other way as well. It says if the third harmonic of an open pipe is 540 hertz, what is the length of the pipe? The velocity is equal to 343 meters per second. That's really common for the speed of sound. It's always around there. Temperature will just vary it a little bit. Now, even though we're not looking for wavelength, this is looking for length of the pipe, I still like to start with the same formula. V is equal to lambda F, and figure out what part of that is going to give us information about the length of the pipe. Well, the velocity is already set, 343. Frequency doesn't have to do with length, but wavelength has to do with length. So I need to figure out that first to figure out the length of the pipe. And in this situation, it's given me the frequency and the velocity. So I just take V divided by F, 343 divided by 540, and I get 0.635185. Okay, and that's in meters for our wavelength. We haven't got to the length of the pipe yet, but that's what's going to give us our information we need for length of the pipe. I'm going to draw that closed pipe again. I keep putting open there. It means closed. We'll look at open pipes in the next lesson where both ends are open, but this one is for closed. So I'll draw that closed pipe here. All right. And now we want to set up that relationship between wavelength and length of the pipe. So it says third harmonic. So I have to remember from that it's going to be up, down, and there, where 3/4 of a wavelength fits inside the length of the pipe. That's the third harmonic. That's the theory part that you need to know. And now since we have wavelength, we can easily figure out the length of the pipe here. We go 0.63518 meters, all right, times 3/4 gives us the length of the pipe. And that's going to round to 0.48 meters or 48 centimeters. Okay, so same thing for that. I like to start with this formula off the start as well for any equation with pipes. Then I have to find out what the wavelength is because that's going to relate to the length of the pipe. Then set up your equation here that relates wavelength to length of the pipe. All right, so I hope that made some sense. Let me know if you have any questions. We will cover open pipes in the next one and then look at strings for our last lesson of the course. So give those practice questions a try and I will see you in the next lesson.